Okay, before beginning my talk, I should acknowledge Dr. Dan Geisler. He contributed to the conception of this research, and we worked together between 2010 and 2015. I feel very sorry that he cannot see the conclusion of this story. Cochlear traveling wave travels 2 to 3 orders of magnitude slower than the compressive wave propagation. So as a compressive wave, it takes on the order of microsecond to travel 10 to 30 millimeter popular animal cochlear models. But in the slow cochlear traveling wave, it takes on the order of a millisecond. So this time domain, this frequency domain, pure tone response is convenient to appreciate the phase velocity. You can intuitively see it takes time, and this impulse response, no, it already began, so I should restart. Right. Impulse response is convenient to feel the group velocity, how the peak moves along the cochlear length. It gets slower and slower as it travels toward the apical direction. Because the onset delay speed of cochlear traveling wave informs about the cochlear traveling wave structure, many researchers dedicated to identify accurately the latency of the cochlear traveling wave, including Mario Rogero. They dedicated a series of investigations to quantify the latency of cochlear traveling waves. This figure is a summary they published in 2012, and it shows the characteristics of cochlear traveling waves. This is the x-axis is the distance, y-axis is the onset latency, and the onset latency monotonically increase toward the apex, and to reach the apex 18 millimeter location of chinchilla, it takes about 3 milliseconds according to their measurement. However, there are a few irregularities that it is unclear whether it agrees with the conventional cochlear traveling wave theory. This gray colored column around the 8 millimeters, there is some hesitation or discontinuity of the onset latency of the measured from different methods, from the noise response and from pure tone responses. And this solid line obtained from click response, they couldn't see any detectable onset latency between 0 to 8 millimeter location according to their measurement. Their time resolution is 4 microseconds. Within their resolution, until 8 millimeters, they couldn't see onset latency. So what is going on in the basal tone of the chinchilla cochlea was the motivation of Dr. Geisler and me. And we noticed the coincidence. Anatomically, the top graph shows the cross-sectional area change along the cochlear length obtained from chinchilla. And as you see, to accommodate large oval window and round window and the basal 1/3, it has large area, cross-sectional area. And after that 1/3, the cross-sectional area is relatively constant. So we called that the large three-dimensional volume at the basal tone a sound port region, and the remainder 2/3 region, tubular region, and the onset latency curve somehow coincide with this anatomical sectioning. That's what we found. This is graphical way to see, although this is still very oversimplified. This is a two-dimensional cartoon, is uncoiled. However, what I try to draw your attention is the location of the oval and round window. Collectively, I call this the sound port. In our conventional cochlear models, including ourselves, the oval window, round window at x equals 0 at the basal extreme. However, in reality, the oval window, round window they are not placed at x equals 0. So we somehow try to interpret this geometrical characteristic of the sound port. So our hypothesis is that in the sound port region of the cochlea, non-traveling wave and traveling wave coexist, is our hypothesis. So we used our model. Our model incorporate three-dimensional organovo-Corti mechanics. However, we are still using what I call the conventional 2D rectangular fluid domain as you see in panel A. Our model include individual hair cells and fine structure, three-dimensional structures, so it's computationally bulky. The model's entire degree of freedom is like a quarter to a third millionth degree of freedom. It's a large model. The degree of freedom is not necessarily much freedom, actually. Some people misunderstand that. Is it a million degrees of freedom? Is a million times more free than the single degree of freedom? Is not necessarily so. Our model has a few dozen model parameters. Not a single parameter has ambiguous meaning. For example, BM, collagen fibers, Young's modulus, transduction channels, the conductance, like that, our model parameters has a specific physical and physiological meaning. So we have developed this model for over 10 years, and what we used for this study is the MoH model. MoH model is nonlinear time domain model. So this is validation of our nonlinear model to the click response. So our model could several qualitative characteristics of physiological observations, including level-dependent impulse responses, frequency responses, as you see in panel B, and compressive nonlinearity. Also, we simulated pure tone responses, reasonable traveling wave patterns, depending on the levels, 45 dB, 115 dB, and dead cochlea. And it shows the reasonable amplification and the compressive nonlinearity. So now I try to modify our model to reflect the reality of sound port location. The locations are here in this cartoon, the over window and round window. We thought that this large volume apply pressure in this three-dimensional space almost instantly. So this red broken line and the green broken line is where we just approximated the pressure hit nearly at the same time. So we just modified the location of our sound port in our rectangular model, still rectangular model. Instead of x equals 0, it was placed over from between 0 and 4 millimeter location. So that's the model. So we consider the three cases. Case A is traditional cochlear model where sound port is at x equals 0, left hand or basal extreme. In panel B, is what we argue is reflecting the geometrical reality of the sound port between 0 and 4 millimeters. And the C is the realistic model is the entire top surface and the entire bottom surface consider the sound port. So we first simulated the impulse response of this model. In panel A, as you see in my first animation, as the impulse applied, this is panel D, shows the x-axis is time, y-axis along the time we show the response at 5 different locations: 1 millimeter location, 2 millimeter location, 3 and 4, 5 millimeter location. So 1 millimeter location response arrives earlier, and 5 millimeter location, it takes longer time for the wave arrives. In panel B, what I argue, realistic model, 1 to 4 millimeter location, because it's widely open, they hit the response immediately, while after 4 millimeter, it takes some delay. It takes some latency to arrive. In panel C, it is widely open, entire length, 12 millimeter length, hit at the same time, so they hit immediately. However, rising time slope is different because the organovo-Corti complex stiffness of gradient. More compliant one is shallow rising slope. So if we calculate in panel H, the onset latency, our traditional model start from 0 and gradually increase, continuously, smoothly increase toward the apex. However, the 0-4 model, what I argue realistic model, it has 0 onset latency until 4 millimeters, and then have a show latency after then. Then we simulated a pure tone response. So this is the 10 kilohertz pure tone simulation, and the panel A here, we see like a reasonable traveling wave response. And what do you expect? I intentionally hit these two responses. Do we expect any difference? So I give you 3 seconds to imagine, to change your answer. Right? Okay, ready? So no difference. Even if the wide change in the opening, this is the traveling wave shape. There's slight difference in fine structure, but overall, it's negligible difference. I said this is active cochlear response, right? What if it is passive cochlear response? Passive cochlear response envelope is broader, right? Which is expected in top plot. And I also hit 2 responses. What do you expect? I'll give you 3 seconds. So it's the same? Change? Okay, let's see. It's a bit confused the traveling wave in this realistic case. And then we see that it is actually overlap of 2 types of waves here. In the last case, entire span sound port case, we separate 2 waves, traveling wave, and I would call standing wave. And that's why panel E was confused. So if we simulate our realistic case for different frequencies, and if we calculate the onset latency, this black line is active onset latency. It increases toward that, and around the 4 millimeter location, there is some discontinuity. And then it rises again. And in passive response, it confuses. It's 0, between 0 and 2, and it hesitates from 0 and non-zero. Because we assume this is a single traveling wave in this method, estimating the group delay. So we compare finally with Mario Rogero's data. The top one is from Chinchilla, and the bottom one is our simulation from Jobber model. So the length scale is different. However, we argue that we reproduced the major characteristics of what they observed. They observed they somehow discontinuity around 1/3 of the length, and we also discontinuity by the click response, which is equivalent to impulse response, 0 onset delay in the sound port region, and then comes in like their curve. And what they didn't observe is that the passive tonal response. So that's considered our prediction. If they have numbed outer cell, probably they see like our light blue color is our prediction. So we wondered what happens. We have also ex vivo cochlear model. Can we remove partial or whole cochlear traveling wave in excised cochlea? So this is our excised cochlear preparation. We isolate the cochlea in A, and we remove apical tone and basal tone, and leaving only a single tone, donut-shaped single tone. And the panel C is the top-down view of the cochlea, and this the pink-colored ring is our target middle tone. And then in panel D is after we cut off the apical tone and basal tone, and then we need to remove the interscale bone. Then we have a large sound port. This red circle is large sound port, and this red asterisk is the top opening, and the green asterisk is the bottom opening. So we create artificial sound port, and then we scanned. This shows that we can scan along the coil of the cochlea longitudinally. We can scan radial section. So in here, we see like CDE, like longitudinal vibration pattern. So next slide will show the pure tone response at the best frequency location. And what we if we believe in what we observed the previous simulation, we expect it will be most likely standing wave-like response. And let's see. Hold on. Oh, no, I need to prepare present this box plot, right? This box plot is of reduced bone is similar to this way. To be consistent with the previous presentation, is red and green opening there, and we observe the response here, right? So red color is the basilar membrane, and blue color in this one is a reticular lamina. We tried hard to see evidence of a traveling wave, and we couldn't see the evidence of traveling wave. It is moving together, flat, as if a standing wave. Next one, then, can we restore the traveling wave? So what we did next is that instead of removal of basal tone, we kept the basal tone intact. Only apical tone removed, and made the hole only apical side. So it's a hybrid. It's not actually tubular structure. It's not actually wide opening the structure. Then what we expect, probably it could be confusing response, some hint of a traveling wave, and let's see. Right, we could restore the traveling waves. To conclude, what our results say is that why do we care about this one, is that any observations relevant to the latency of cochlear traveling waves, including cochlear tonotopy, tuning quality, autoacoustic emissions, might be confounded if there exist standing waves in the cochlea. You interpret the result mixed standing wave, traveling wave, with the framework as if there are only traveling waves. Thank you.
Okay, we have a couple of minutes for questions.
Pardon? Okay, so this is a very, very interesting argument you're making, and I partially agree with you, but I have an alternative explanation based on data. But it shows this pi phase shift. You're seeing a pi phase shift? Is that what it is? Seeing the reversal in the phase.
Right, yes.
And that's, you're looking at the phase, and so if you take the frequency derivative, you get the group
Yes.
delay. So my paper is published in JASA. The title is A Second Cochlear Frequency Map that Correlates Distortion Products and Neural Tuning Measurements. And this pi phase shift was observed neurally way back when, and it differs from what you're seeing is that if you do the experiment at a slightly different frequency, the pi phase shift moves with the CF. So that's why I call it a second cochlear map. So in some ways it's agreeing with what you're saying, and in other ways it's just a partial explanation, but I want to talk to you.
Okay, thank you for your input.
That was John Talland, by the way. Please say your name.
Paul Colston. Lovely talk. I particularly like any talk with an animation. The first two animations you showed at the start, am I correct in thinking that the lower one was showing the fast traveling wave?
This one?
The introduction to your talk. You showed the propagation of the slow wave at the top.
Yes, yes.
And the one at the bottom, is that the fast traveling wave? Is that what that was showing or not?
No, there's no fast traveling wave here.
Okay, thank you. I don't have a question then.
Julien Amo, I liked your simplified approach for the modeling, where you take this very simplified geometry. But then I'm wondering, what about when you show initially, the shape of the duct is increasing in area toward the base. The round window is only a very small part of it, which is not like what you did in your model, right? Where you have a straight round window that is pretty long.
Right.
How much do you think that would affect your results?
I do not know. However, the reason I stick to rectangular shape, if I make it three-dimensional or cross-sectional area change, we are not sure. Is sound port to location effect or geometry changing effect? It becomes unclear. So intentionally, we start from here just to see the sound port location effect. That's the next thing we can do.
Thank you.
One more very, very quick question.
Very quick. Sunil Puri. So clearly anatomy is always important, so that when you're modeling, the especially in finite element, you want to figure out the layout. And so you show the possible importance of the round window being not at the end, but in fact, I always remember that in the cat, the round window is like in the middle of the cochlea practically, right? And so I've always wondered about that, and so I'm glad you're looking at it. So, but then I was confused. In the active cochlea, it doesn't seem to matter, but in the passive cochlea, it does matter. So, what's your guidance on that?
So in active cochlea, probably outer selection, as you might agree with the Y-shaped structure, probably favor for formulation of traveling waves, and it somehow overcome the standing wave component, and you need to further study it, right? Yes.
Okay.
Yeah,
Thank you.
we have to move on. Thank you so much, Johnny.